I'll be talking about the EAS working system. From the picture, we have seen how it's been structured, the standard one. And the EAS system is a kind of system that is used in shops or library where there are merchandise or books that are supposed to be protected. And the main function is that it's supposed to function as an anti-theft system, whereby any article that has not been deactivated cannot be taken out. What it does, from the diagram, we have seen the component contains a transmitter and a receiver. And any article that is being brought closer or that is about to be taken away that has not been deactivated, it sends a signal, and this signal is being transmitted to the receiver, and this is kind of bring about an alarm, whereby it's being known that something is happening here. From what is being written, the EAS system produces an electromagnetic energy around where it is. It creates an electromagnetic zone. When you are approaching it, that's when it triggers the alarm. And from our own design, we have a skeletal something, apart from the standard one. And this that we have used to be able to create the distance from where it would trigger, from where the system would trigger, and we hear the sound of the alarm. What we did was that we placed our measurement by the side of the magnetic line, close to this pole. That's where we have a very sensitive, most sensitive of the pole, where it could be measured. And we try to bring in a scale so that we could know the resistance and the distance from the EAS system. And what we got was that the higher the ohms, the lesser the distance. They walk in opposite direction. And this is our result from our calculation. When the resistance was 0 ohm, the distance, it triggers at a distance of 10.5 centimeters. And the more we increase the resistance, the lesser the distance. And at 30 ohms, the distance is too short. And this is the graph that we have plotted against it. And this is what I've explained before, to say that the range of the ohms is, it triggers between 20 and 30 ohms. And we think it should go less than 20 ohms from 120. What we're trying to explain here is that it has to go from dryness to wetness, and we're trying to calculate for the wetness of wetness of the RF tag. That's what I'm just explaining. And we did some capacitor tests, and we noticed using the areas of we tried to check the area of the capacitors using sides of 1.5 by 1.5 on photopaper scotch, and our result shows 100 picofarad for the capacitance. And the same thing we did for 2.5 by 1.5 on epoxy, and it showed our result was 8 nanofarad. And these are the design for the capacitors that were used. And again, we did, for the last one, we calculated the capacitors for 1.5 by 1.5 meter area on aluminum foil, because we have done on tape before. And these are the results that we got. And at the end, we did on back side of the foil, which was used as dielectric, joined with LV, and that result gave us about 100 picofarad. So in all, we think coupling capacitors work better with the area of 2.5 by 2 centimeter to produce the results of 200 picofarad. Okay, continue.
Here the design part. We have discussed design of the coil. Before that, my friend discussed we have design or circuit, design and manufacture and then implement. So for the design part, we will try to print the low resistance coil with gold ink that has less resistance. There are different kinds of ink, but we